Hello. Hello. Okay. So good evening, everyone. Today we're going to start the week 4 of fluid flow operations. So let's start. So I think my screen is visible. Yeah. So first I will go through what Sarah has taught this week, just a recap. Then I will tell something else. I will do the revisions in detail and we'll do some problems on that. Okay. So today's session is all about the basic equations of flow. Okay, so we are mostly talking about one-dimensional flow because, like when in the last class we have seen that the pipe flow is a one-dimensional kind of flow, right? Because the velocity is changing only in the x direction. The flow is happening in the x direction, so that is a one-dimensional flow. So we will mostly discuss around that. Okay, so for what type of basic equations in fluid flow are required, that we'll see. Okay, so first will come the mass balance equation, then comes the momentum balance equation, then comes the energy balance equation. Okay, so this is talking about the conservation of mass. So this is the continuity equation for 1D unsteady flow. So I will be explaining it in a little bit different way from what sir has taught, but it is the same thing. The final thing will be coming same. So let's start that. Okay, I will be coming back time to time with these equations and lecture. Okay, let's start. So first one is what about? So suppose we call it as a like our system. So what is system? So system means system means definite amount of definite amount of easily identifiable mass. Okay, so generally in our in fluid calculation we consider, suppose from a big chunk of fluid or liquid which has a regular shape, we consider a small 3D structure or small square or maybe small sphere kind of thing. So that is our system. Okay. So this system follows generally three laws. So first one is the conservation of mass, right? Conservation of mass means mass is what? Mass is the like how much kg. The unit of mass is kg. We all know that, right? So this is dm dt of this system is 0. That is the conservation. That means the mass is not changing over the time. Suppose a fluid is flowing from, suppose there is a fluid there and there is an inlet and there is an outlet. Fluid is coming, fluid is going out. So even if the fluid is flowing, the total mass of this system is not changing with time. It is remain same. So this concept is called the conservation of mass. Next one is the conservation of linear momentum. What is that linear momentum means? So what is momentum? Momentum we know as, so momentum is momentum means, suppose P is your momentum, P is mass into velocity. So what is the unit of momentum? Kg meter per second, right? So this is your momentum unit. So since previously also we have seen that conservation of mass means mass is not changing with time of the system. Then linear moment, that means conservation of linear momentum means linear momentum is also will not change with time. So it is dp dt equals to of this system is 0. And what is this? Rate of change of momentum means, so from the unit, rate of change of momentum means kg meter per second square is coming, and we all know that kg meter per second square is an unit of force, right? So F is equivalent to rate of change of momentum, and this is, and what is this force? This includes all type of force, all body forces and all surface forces. So body force means what? Body force means something which can actually work without any physical contact, right? Like gravitational force. So there is always a gravitational force. So this is a body force. Then suppose you are in an electric medium or some particle is in electric medium. So this electrical force. This is your body force. Magnetic force. This is your body force. And what comes under the surface force? So Fp is the body force and Fs is the surface force. Okay, so this surface force includes shear force, because we all know that we have learned about shear stress, right? Tau. So tau works at the surface only, right? Tau works at the surface. So this is the surface force. There is a surface tension force. Surface tension force also works at surface, right? So these, there are other surface force and body force also there, but mainly these are the common one you can relate to. So this is the conservation of linear momentum. Third one is the conservation of energy. Conservation of energy. Energy we generally denote it as dEdt of this system is 0. So what this E includes? So rate of change of energy. Rate of change of energy means, from thermodynamic perspective, you will know Q dot heat or work done is equals to dEdt. That means Q dot means rate of change of work given or heat given, whatever it is, rate of change of, and W dot means work done. And there is always a loss related to it. This loss is defined as the conservation of energy. Okay. And this E includes all type of energy, like U means internal energy of any system, EK means kinetic energy of any system, and EP means potential energy of any system. So this all things comes under the conservation of energy. And Q dot, if Q dot is greater than 0, suppose Q dot is rate of work given is greater than 0, that means heat is given to the system. Heat is given to the system, and W dot greater than 0 means work is performed by the system. Work is performed by the system. Okay. So now suppose, think N. N is an arbitrary extensive property. Okay. Which depends on mass. Which depends on mass. That means it has some kind of unit related to kg. Okay. And there is another property which is eta. Eta is the respective intrinsic property. Excessive property means it contains mass, and intrinsic property means it does not contain mass. Something is divided by mass. That means this is N by M is your eta. Okay. When something is divided by its own mass, that is the intrinsic property. So what can we write from this in the differential form? So N is summation of all these intrinsic property into differential mass of this system M, right? So N is the excessive property which contains mass, and eta is the intrinsic property. So if this intrinsic property is multiplied by some differential mass and we are integrating it over the whole system we are considering, that is your excessive property, right? And now what we can write from dm? Mass is density of the system into volume of the system from the definition. So it is, so if we consume the volume of the system, so we are writing a volume like this because we have to write velocity also v and volume v, so that will be confusing for you. So we are writing volume v like this. So volume v is this, and eta dm means rho dv. So volume of like volume can be changeable. Density is the property of a system which will not change over the area. So that is why it is constant for a system, for a same system. So this is how we can represent it, right? Now if we consider conservation of mass. So now if we consider conservation of mass. So M is our extensive property, right? And so how can we represent M? So mass can be represented by density into volume, right, of this system V. So if we compare with the previous expression, now suppose N is your M, right? That means M is your extensive property. So now suppose N is your M. Then what is eta? If you compare with this, what is your eta? So eta rho dv it is written here. Here it is written rho dv only. So eta is your 1, right? Eta is your 1. Similarly, for linear momentum case, P, right? P is, we have said momentum means mass into volume, right? Mass into velocity, sorry, mass into velocity. So we can write mass like this, rho dv, this is mass, into velocity is your v, right? All these things are vector. Obviously I'm not giving vector sign, don't confuse. So what it is, if you write like this in an eta system, what will it be? So if you compare, so here rho dv is same as it is, eta is your v. So now if n is the linear momentum, then eta is your v, that is velocity. It will be much easier for you to remember, right? Similarly, for energy conservation, suppose E is there, So E will be total energy per unit mass, and this is your mass, right? E is this intrinsic property of the energy. So here N is equivalent to E and eta is equivalent to small e, right? So if we remember, if V is this velocity and here E is your energy per unit mass, right? So if you, in the case of velocity also, if you remember, P is equals to mv. So P is the extensive property, and for eta it will be divided by m. That means only V will be left, right? So V is this velocity, E is this energy term, right? So, and what is this E? In this case, E also like E concludes or includes everything: internal energy, kinetic energy, and potential energy. So we know the expressions of also. So E is, U is the like energy per unit mass, internal energy per unit mass. I am not writing internal energy plus unit mass plus V square by 2, that is kinetic energy plus unit mass plus G Z, potential energy per unit mass, right? Units are coming same. It is energy per unit mass. It is m square plus s square it is m per second square into m, right? So it is also a meter square per second square, right? So this is your energy per unit mass. Okay. So now all this equation, more generalized flow equation, is called the Reynolds transport theorem, and from there only you will get all these equations, all these expressions of the equations what sir has done in the class. I'll be doing one by one. Okay. So the more generalized equation is Reynolds transport theorem. Okay. So what does it talk about? So it talks about the system, or we know what system is, right? System is the basically identifiable mass, easily identifiable quantity of anything. And what is control volume? Certain region of space in which we are interested to analyze. This is your control volume. You will see the expression that why this is important. So suppose now at time t equals to 0 or time t equals to t0, there is a control volume, suppose a random shape, right? The whole thing is, so this is your control volume, okay? And some fluid is passing through this, okay? This is your control volume and this is your whole system, okay? This is your system. After some time, at t equals to t0 plus delta t time, you will see that your control volume will remain as it is, but your system moves and flow is happening like this, okay? So how will you define this in the form of equation? And what are changes can happen? And all these things is like all these changes are related to your mass, the system mass, the mass of the system, the momentum of linear momentum of the system, and the energy of the system. So how will we define it? So this extensive property, so that means, so rate of change of any extensive property in this system is equals to the, so this is, I am writing the definition also, rate of change of any arbitrary extensive property in the system, right? So this is, suppose flow is happening through this and system is changing. Like what is changing? We are thinking mass is changing, linear momentum is changing, and energy also changing. So how will you define that? Like what points are there to consider? So d and dt is the rate of change of any arbitrary extensive property in the system. Okay. This is the, so this is del n del t of the control volume. This definition is rate of change of same extensive property, same extensive property of control volume. So control volume means we have seen here what is control volume, the certain region of space in which we are interested to analyze, because we cannot analyze the whole system together. So we are thinking a small part of the system or small cube of the system, small sphere of the system we are considering, and we are integrating it to the whole system. So that is our control volume. So to calculate the rate of change of any arbitrary extensive property in a whole system, we have to first consider what is the rate of change of that same property in our interested region, that is our control volume, right? And plus net flow rate of the same property throughout the control surface. So flow rate is defined like this, right? Flow rate means, so if you see, this is the kg per meter cube, this is meter, and this is your meter square. So this is kg meter per second, right? No, this is kg by meter per second, right? So this is the flow rate. Basically mass flow rate I'm talking about. So this is this over the control surface. So this is the net flow rate of the same property. Suppose we are considering mass as our extensive property, that net flow rate of this mass out through this control surface. So this is the Reynolds transport theorem represent in this form of diagram or schematic if you call it. So your control volume is moving, system is there, your system is moving, control volume is suppose a small part of it, and how the change is happening, this can be defined by this basic equation. So this is the rate of change of total rate of change of the extensive property system is the rate of change of this extensive property in the control volume, and how much net flow is happening at the control surface. That summation will give us the total rate of change of property in the system. So now what is this del n CV dt? So if you expand this, what it will come? So rate of change of extensive property, okay, rate of change of extensive property in the system is del n control volume of del T plus the net flow rate. through the control surface. This is eta rho v dA. This is the mass flow rate. This is the mass flow rate, kg per second. So this dNdt system and del control volume, in the control volume, how this n is changing, this can be written as del T of integration over this control volume, the intrinsic property integration, right? So eta rho dV. So that is what we have seen here, right? So this is the extensive property can be written in the integral form with the intrinsic property is integrated over the mass of the control volume or over the system, right? So now this del NCV del T can be written like this, plus it is as it is over the control surface eta rho v dA. So this is the working formula of Reynolds transport theorem. It is very important to remember. Now we will substitute. So now we are coming to conservation of mass, right? So now I'll do one by one the conservation of mass. So conservation of mass was conservation of mass. So what is that? We have seen that dm dt equals to 0 and n is equivalent to m and eta is equivalent to 1, right? So now we will replace this in this equation of Reynolds transport theorem. So dm dt equals to 0 means left hand side it will be 0 equals to del T of control volume integral over control volume rho dV because eta is 1 plus integration over control surface, it is rho V dA because eta is again 1, right? So this is the equation of conservation of mass. Now suppose there is an assumption we are taking. Or maybe we don't want to take the assumption right now. So this del T of rho dV is limits of the triple integral are independent of time. So del T, if you are considering the first term only, del T of rho dV, right? So from Leibniz theorem, there is a Leibniz theorem. Leibniz theorem. If you look into it, it says, suppose del x, it is to be integrated from a to b, and there is a function f which is a function of x and y dy. So this will be equivalent to del f del x dy integrated will be from a to b. So similarly, this rho is a function of both volume and time. And if this a and b have to be independent of x. So this can be written for this left hand side part also. So this will be equals to integral over CV control volume del rho del T into dV, right? And what about the right hand side part? So the right hand side part will apply Gauss divergence theorem. So what was there? CS rho V dA, right? Rho V divergence dA. So if you apply Gauss divergence theorem, what it will come? It will be control volume divergence of rho V and it will be dV, right? So this is the Gauss divergence theorem. Gauss divergence theorem we have learned already, so I am not explaining it again. So now what comes? Now what are the terms left? So after combining these two terms, what it will come? It is 0 equals to, you can now take the common of control volume, and it is the del rho del T summation of del rho del T plus divergence of rho V whole bracket dV, right? If you combine these two, you know. So this is the del rho del T dV and this is the divergence of rho V dV. So now this will come as del rho del T plus divergence of rho V equals to 0. So this is your this is called continuity equation or conservation of mass in a flow field, and it is valid anywhere for any system. So this is your continuity equation. Okay. And now if we are considering it as a like incompressible flow, for incompressible flow, you already know that change of density with time is very negligible, so it is almost zero, right? So you can ignore the rho here, like density term here, and what it is left? It is only left with divergence of V equals to 0. So this is the typical, because in our analysis we mostly consider incompressible fluid for the easy calculation. So this is our one of the main equations, like momentum of conservation of mass means the continuity equation, which is divergence of V equals to 0 in case of incompressible fluid, right? Next comes the conservation of mass, conservation of linear momentum, sorry. So here it means that linear momentum is a rate of change of linear momentum is the force. So F is, we have seen F equals to body force plus surface force is equals to rate of change of the linear momentum of the system, right? Now if we want to write it in the form of Reynolds transport theorem, what it will be? So, and we also know that here n equals to p and eta equals to v. So what it will be? Like, so del n del t of this system equals to del n control volume, or not, right, like this, del t of control volume eta rho dv plus control surface eta rho v dA. So now if you replace this, so dp dt of the system is equals to body force plus surface force equals to del t of control volume. Eta is your velocity, that is velocity into rho dv plus control surface velocity into rho v dA, right? So this is your conservation of linear momentum. Now if you write it for like your x momentum balance equation, or if you want to write it for x, so what it will be? So suppose you are writing it for x axis. So all the terms will be in the name of x. So fbx plus fsx equals to del t of control volume. So in the x direction the velocity is u rho dv plus control surface will come as u rho v is a vector and dot dA, right? Only u will be there in the v because we are considering the x direction also. But in case of, but this v will not change because it is inside the divergence term, right? So it has to be this, it has to be in the vector form. So if your v is like this, ui cap plus vj cap plus wk cap, then you can write this. So this v is for like u direction, x directional. This v is also for x directional, but this v is inside this divergence term, so that has to be in the divergence form, right? So we are taking the vector there. Similarly, for y-axis and z-axis, you can write. Right? Now comes the final one, that is the energy conservation. So for energy conservation, you know that this n is your E, from the Reynolds transfer train, eta is your small e, right? And this rate of change of E equals to the change of heat given and the work done by the system. So you can write this, I am writing directly. So this dE dt of this system equals to q dot minus w dot equals to, it is the del T of control over control volume E rho dV plus over control surface, it is E rho V dA, right? So now this W can include many things. So now this W, or work done by the system, can be WS, which is the shaft work, plus W normal, which is the work done by normal force. Work done by shaft work done by normal force. Next comes the W shear, work done by shear force. And fourth one is the W other, all other works. Okay. Okay. So this is the energy conservation equation. We will not go into the details of the equation. We will now proceed. And then there is main again one more important equation, that is the Bernoulli's equation. So Bernoulli's equation is general form of Bernoulli's equation is this is the potential head P1 by rho. This is the kinetic energy head. This is the overhead. This is the work done, plus 2 by rho plus alpha 2 V2 square by 2 plus GZ2 plus HD. This is the total head loss. This is the most generalized form. We are using the part of it. Okay. So these are the basic equations we are going to deal with in this week of assignment. So now we'll proceed to the equation part problem solving part. So first question is, the continuity equation is based on the principle of conservation of mass, conservation of linear momentum, conservation of angular momentum, or conservation of energy. So you can tell me, I am waiting. So we have seen here like from where the continuity equation came. So continuity equation came from the conservation of. So this is your continuity equation. This has come from the conservation of mass, right? So what will be your answer? So this is the conservation of mass. Next, two pipes of diameter d and 2d respectively converge into a third pipe of diameter 4d, right? If the velocities of an incompressible fluid are v1 and v2 and in the two pipes respectively, what would be the velocity of the fluid in the third pipe, right? So we know that. So what is happening? It is happening A1 V1 plus A2 V2 equals to A3 V3, because two pipes of diameter D and 2D are converging into third pipe 4D, right? So A1 is the pi D square by 4 into V1 plus pi 2D square by 4, that means 4D square by 4 into V2 equals to pi 4D means 16, right? 16D square by 4 into V3. So what is coming? Like pi can be cancelled out, D square can be cancelled out. So it is V1 by 4 plus V2. So we are cancelling pi D square from everywhere. So what is left with is actually V1 by 4, V2 equals to 4V3, right? Four V3. So now we are doing like V1 plus 4V2 equals to 16V3, and V3 will be then V1 plus 4V2 by 16. So this is your option C. right? V3 equals to V1 plus 4V2 by 16. Okay, this is your answer. Next, what is the correct form of the continuity equation for the 2D steady flow of a compressible fluid, right? So for the compressible fluid, we have seen the equation as del rho del T plus divergence of rho V equals to 0. As it is said, a steady flow, so only divergence of rho V equals to 0 will be there. So for like 2D states, so for 2D it will be del rho U del X plus del rho V del Y equals to 0. So it is del rho U del X del rho V del Y equals to 0. So this is your correct answer. Next, in a 2D steady flow field, the velocity of an incompressible fluid along the x-axis is given by u equals to kx square plus ky square, where k is a constant, right? If v equals to 0 at y equals to 0, find the velocity along the y-axis. Okay. Yeah, excuse me. So, from incompressible fluid expression, so incompressible fluid, it is said, right? So, we can write the continuity equation like divergence of v equals to 0. That means del u del x plus del v del y equals to 0, right? So, del u del x means from the expression you know expression of u. So, it is 2kx, right? 2kx plus del v del y equals to 0. So, del v del y equals to minus 2kx, then v means integration, that means minus 2kx y plus fx, like a constant basically. So already said that if v at y equals to 0, v equals to 0. That means fx is coming as 0. If you consider fx means, or you can consider it as a c also. So c is your 0. So the expression is v equals to minus 2kxy. So this is option 4. Right? Next. A fluid flows at the rate of 150 meter cube per hour inside a pipe of diameter 0.5 meter. Find the velocity of the fluid if the diameter reduces to 0.25 meter for the same flow rate. Okay. So, what is given? Q is given basically. Flow rate is given, right? So, Q equals to meter cube per hour, right? It is a meter cube per hour. So, 150 meter cube per hour. That means it has to divide by 3600 to become meter cube per second. Then only we write it Q equals to VA, right? So for the first pipe diameter is 0.5 meter and find the velocity of the pipe when it is reduces to 0.25 meter. So now we know the Q, that is 150 by 3600 equals to V into A. A is pi 0.25 square by 4, right? Now what is the V? So for this we have to calculate. One 50 by 3600 into 4 by 3.14 by 0.25 a whole square. It is coming as 0.849 meter per second. Yes, so it is close to 0. This one. Option A. Done. Next problem. In a 2D steady flow field, the velocity of an incompressible fluid along the x-axis and the y-axis are given. Which of the following conditions should be satisfied for the flow field to be continuous? That means continuous means it follows continuity equation. So for an incompressible fluid, same del V divergence of V equals to 0, del U del X plus del V del Y equals to 0. So del U del X is A Y and del V del Y means if you differentiate it, it will be 2cy, right? 2cy equals to 0. So it will be A plus 2c equals to 0. So option 3. Next, which of the following conditions are not necessary for the application of Bernoulli's equation? Inviscid flow, incompressible flow, steady flow, none of the above. So all of these options or all of these conditions are necessary for Bernoulli's application. So that's why this is the none of the above. Next, which of the following relationships is correct? Stagnation pressure equals to dynamic pressure plus static pressure. Static pressure equals to dynamic plus stagnation. Dynamic equals to static plus stagnation. Tell me. So it is the stagnation pressure means dynamic plus static pressure. Option A. Next. Assuming that Bernoulli's equation is valid in the case of a horizontal streamline, what would happen to the pressure if the velocity is doubled? So, what is the Bernoulli's equation? So, So from the exact form, if you want to write, so you can write it from this equation, from such lecture only. So this is all I talked about already. The sum of the equations or problems he has solved. Let me go through this. In the lecture 8, it is the linear momentum. So here comes the Bernoulli's equation. So this is your Bernoulli's equation expression. Velocity head, pressure head, and potential head. This is. So now suppose we are doing the answer. So it is like P1 by rho g v square by P1 square by 2g plus z1 equals to P2 by rho g plus v2 square by 2g plus z2. So it is said that in the case of horizontal streamline, that means z1 and z2 will be cancelled out. Pressure to the happen to the pressure if the velocity is doubled. So if v2 greater than v1, right? If v2 is greater than v1, suppose I am like writing like this: p1 equals to uh, p1 plus half rho v1 square equals to p2 plus half rho v2 square. So p1 minus p2 will be half rho v2 square minus v1 square. So it is said that velocity is doubled. So it is 2v1 square, right? 2v1 square. So if v2 is greater than v1, pressure v2 is greater than v1, that means it has to be this is a positive term. That means this has to also be a positive term. That means P2 has to reduce. So P2 must be less than, because has to reduce. So P2 has to reduce. So when the fluid velocity is increased, pressure has to be reduced. So pressure gets reduced. Option A. Next. For the flow of a real fluid, across a large cross-sectional area, which correction factor has to be incorporated into the Bernoulli's equation? So, for a large cross-sectional area and the real fluid is there, in Bernoulli's equation, the kinetic energy correction factor needs to be added. that is alpha V1 V1 square by 2g term. This is what I have written in the generalized form like this. This alpha has to be included. Next, according to Bernoulli's equation, the total head in a horizontal nozzle can be expressed as the sum of velocity head and the pressure head, because in the horizontal nozzle there is no potential head. The Z term will not be there, right? So here Z term is not there, right? So this will also be not there because it is a horizontal plane. So velocity and pressure head. Option A. Next, water flows through a horizontal pipe of diameter 0.5 meter at a flow rate of 0.1 meter cube per second. The pipe tapers into a, so this is the tapering problem, like this. Tapers to a 0.2 meter diameter towards the other end. The pressure at the wide end is 20,000 Newton per meter square. Find the pressure at the narrow end. Neglect the losses and any external head. So it comes from the Bernoulli's equation and it is in the same horizontal pipe. So the equation will be P1 plus half rho V1 square equals to P2 plus half rho V2 square, right? So P2 minus P1 will be half rho V1 square minus V2 square. So P2 will be P2 minus 20,000 equals to half rho is water because like 1000. V1 square is 0. Oh, so we have to calculate the V1. So V1 will be coming from the Q. Q will be V1 into A1 or V2 equals to A2. Right? So V1 will be Q by A1. Q is 0.1 by pi 0.5 square by 4. So V1 is coming as 0.509. So it is 0.509 square. Minus V2 square is similarly, V2 is 0.1 by pi 0.2 square by 4. So it is 0.114 by 3.14 by 0.2 square. So it is 3.183 square. Three point 183 square. So what is coming? So P2 is coming 15063.79 Pascal or Newton per meter square. So this is closest to option D. Next, for the inviscid flow of an incompressible fluid through a pipe of uniform cross section, the pressure drop will be inviscid flow, an incompressible fluid through a pipe it is going and uniform cross section, so pressure drop will be 0. So it is 0. A large tank is filled with two immiscible liquids of densities ρ and 2ρ as shown in the figure. There is a small opening at the bottom of the tank. Find the velocity with which the bottom fluid exits the tank. So the pressure at the bottom. So first we'll calculate the pressure at the bottom. So pressure at the bottom is P0 plus rho GH of the first fluid and 2 rho GH for the second fluid. So it is coming as P0 plus 3 rho GH. So at the bottom point or at the exit, if we apply Bernoulli, so it will be P0 plus 3 rho GH equals to P0 plus half rate, like there is a kinetic energy associated with it, half rho V2 square, half 2 rho V2 square. Yes. So what will come? So 3 rho GH equals to rho V2 square. So V2 square is 3GH. So V2 will be root under 3GH. Option B. Next, obtain the fundamental dimensions of linear momentum. So we have said that linear momentum is the mass into velocity. So it is kg meter per second. So it is ml t to the power minus 1. Option C. Next, a container of diameter 1 meter is filled with water around the center with a constant angular velocity of 15 radian per second. What is the net torque on the container about the center? As that, like rotating, as a container of water is rotating, right? As a container of water, that so torque T tau is alpha I into alpha, right? So as It is a rotating container already, that means alpha equals to 0. So the net torque will be 0. Option C. Option B, sorry. Next. Water flows into a pipe of diameter d with a velocity of 4 meter per second, and suddenly it encounters a diverged section of diameter 3d as shown in the figure. Calculate the expansion loss. Yeah. So we can calculate V2 from the expression A1 V1 equals to A2 V2. A1 is like pi d square by 4 into 4 equals to pi 9d square by 4 into V2. So it will be coming as 4 equals to 9 V2. So V2 is 4 by 9 is close to 0.444 meter per second. So now this head loss can be counted as V1 square minus V2 square minus V2 square by 2g. So V1 square was 4 square, sorry, V1 minus V2 whole square it is. So it is whole square. So it is 4 minus 0.444 by whole square by 2g equals to 0.644 meter. So it is option D. Next. The efficiency of a propeller can be obtained. How? What is the correct answer? So it is the propulsive power by power imparted to fluid. Option C. Next, a jet flow rate and diameter strikes a stationary plate at an angle theta equals to 45 degrees shown the so Q is given, diameter is given, and the angle is also given. Find Q1 and Q2. So from the well established equation, Q1 equals to Q by 2 1 plus cos theta is equals to 0.3 by 2 1 plus cos 45 basically. So it is 0.256 meter cube per second. So it is 0.256 meter cube per second. Similarly, Q2 will be Q by 2 1 minus cos theta. It will be 0.0439 0.0439 meter cube per second. It is option B. Next, the expansion loss is known as border Carnot head loss. Right? We'll be doing some other problems also. So I'm doing it a little fast. Okay. Which basic equation is known as the principle of conservation of mass flow. So you know that it is the continuity equation. Next, for an incompressible fluid flowing through a pipe with varying cross sections, if the cross sectional area increases, the velocity will decrease, because we know that A1 V1 equals to A2 V2. So if A2 increases, V2 has to decrease. Next, what is the value of the kinetic energy correction factor for laminar flow? So it is 2. So alpha is 2 for laminar flow. Bernoulli's equation is applicable under which of the following conditions? Unsteady flow, viscous flow, flow along a streamline, compressible flow. So it is the flow along a streamline, because it has to be steady flow, inviscid flow and incompressible flow. Which of term represents the pressure head in Bernoulli's equation? It is the P by rho g term. It is the pressure head. Next, what is the unit of this P by rho g? So P is the Newton per meter square. This is kg per meter cube. This is meter per second square. Now, Newton is, how this term will come, I will tell. Like pressure head means it will be in meter. Newton means kg meter Newton means force. Force is m into a. So kg into a is acceleration, meter per second square by meter square. Right? This is your pressure. Then comes kg meter cube. Then comes meter into second square. So kg meter second square, and this meter square will cut, 1 meter will be there. So it is the pressure head. Next, a pipeline tapers from a diameter of 8 cm to 4 cm. The volumetric flow rate of water is this. Calculate the average velocities at both sections. So it is very easy. So it is Q into A by Q equals to V1 into A1, right? So calculate the average velocity. So V1 equals to Q1 is 0.1 by pi. 8 centimeter means 0.08 meter square by 4 equals to, it is the around 19.9 meter per second, and V2 will be similarly 0.1 by pi 0.04 square by 4 equals to 79.6 meter per second. Okay, so these are the two answers. Next. Liquid flows in a horizontal pipe at a rate of 0.05 meter cube per second. The pipe tapers from a diameter of 0.3 to 0.2. If the pressure at the 0.3 meter section is 98,000, calculate the pressure at 0.2 section. So neglect this type of problem I have done earlier also. So again I am doing. So you have to first calculate the V1 and V2. So V1 is 0.05 by pi 0.3 square by 4 equals to 0.707 meter per second. V2 is similarly 0.05 by pi 0.2 square by 4 equals to 1.592 meter per second. Now comes the Bernoulli loss, because it is in the same horizontal pipe, we'll ignore. So it is P1 plus half V1 square equals to P2 plus half V2 square, rho V2 square, sorry. So this P2 will be P1 plus half rho V1 square minus V2 square. If we put all the values, we'll get, I'm calculating directly. So it is coming as 97,082.69 Pascal. So here we have taken rho equals to 1000 kg per meter cube, that is of water. Okay, so this is your answer. Next, a jet of water with a flow rate this and velocity this strikes a stationary plate at an angle this. Calculate the force F, right? So if you go through the text, like the session of this week from such lecture, so it will find that the force is the rho qv sine theta, right? So it is rho means 1000 because it is water, q is 0.12, v is 244.46 into sine 60 degree. So it is coming as 25,405.028 Newton. Okay, this is your answer. Next, the Borda-Carnot equation is used to calculate which type of energy loss? So we have done this earlier. So it is the loss due to sudden expansion. Next, in a jet pump, the pressure difference is always positive. Option C. Next, the propulsive power of a propeller is defined by, tell me what? It is the thrust into change in velocity. Next, a pitot tube is an instrument primarily used to measure the potential head, total mass flow rate, static and so it is the static and dynamic pressure based on the Bernoulli's principle in a streamline. So which of the following is an auxiliary equation required to solve compressible fluid problems? It is the law of thermodynamic properties. Next comes again the mathematical problems. So water flows through a pipe of diameter d1 which suddenly expands and the velocity of the smaller pipe is this. Calculate the expansion head loss. So you already know from A2 and V2, right? So it is A1 V1 equals to A2 V2. So it is the pi 10 square by 4 into V1 equals to pi 20 square by 4 into V2. V1 is given as 4. So equals so that for V2 is 4 into 100 by 400. So it is 1 meter per second. And head loss H is V2 minus V1 whole square by 2g equals to 4 minus 1 whole square. Sorry, it is again I have written wrong. This is head loss means 1 minus 2 because it is expanding, right? So velocity will be reduced. So this is 4 minus 1 whole square by 2 into g, which is coming as 0.4587. 0.4587 meters. Next, an aircraft propeller moves at a velocity u. The propeller accelerates the surrounding air, increasing its velocity by an additional u. Calculate the efficiency propeller. So the efficiency propeller definition is given, eta equals to 2 by 2 plus u by capital U. So 2 by 2 plus 10 by 50, which is coming as 2 by 2 plus 0.2. So 2 by 2.2 basically. So it is 0.909. That means 90.9% efficiency has been increased. Okay. A pump with 80% efficiency delivers oil to a tank 25 meter above the source. If the pressure at the source is this, the source size is 4 meter. The total system head loss is 1.5 meter. Find the head supplied by the pump. So it will be coming from the modified Bernoulli's equation. Modified Bernoulli's equation is P1 by rho g plus V1 square by 2g plus Z1 plus head supplied by the pump equals to P2 by rho g plus V2 square by 2g plus Z2 plus head loss h. So it is, as the velocity is not mentioned and it is talking about the large tank, so V1, V2 will be 0. Okay, so there is no kinetic head, right? P1 is 4.5 kilonewton, means 4500 Newton by, this is water or what? This is oil. So specific gravity is, specific gravity of oil is like 0.9. Then that means density is 900. 0.9 into 1000. 900 into G is 9.81 plus V1 square is 0. Z1 is 4 plus HE needs to be calculated, equals to P2 is 0 because it is opening at atmospheric pressure. V2 is also 0. Z2 is 25 and head loss is given as 1.5. So HE is coming as it is coming as 21.99. So head supplied by the pump is 21.99 meter. Next, which equation relates the torque on a rotating body to change the angular momentum? So it is the option B, T into angular acceleration, I alpha. Next, in a curved tube, the additional factors must be considered to calculate the torque. What does it depend upon? It depends upon the pressure components and radius. Next, for a jet striking a moving plate, the relative flow rate reaching the board is calculated as option B, Q dash equals to Q into V minus U by V. So, water enters a pump impeller at radius r1 and absolute velocity this and at an angle alpha 1, and it leaves at r2 alpha 2, and all these are mentioned. If the mass flow rate is 50 kg per second, angular velocity is 120 radian per second, calculate the torque and the power. So, identify torque equation. The torque equation from the lecture note we know it is as T equals to m into r2 v2 cos alpha 2 minus r1 v1 cos alpha 1. So it is 50 into r2 is 15 into v2 is 30, cos alpha 2 is like cos 60, minus r1 is 0.1, r2 is 0.3, sorry, 0.1 into v1 15 into cos 20. So what it is coming? 0.3 into 30 into cos 60, 4.5 minus 0.1 into 15 into cos 20, that is 3.09 into 50. It is coming as 150.52 Newton meter. This is the torque. And what about the power? Power is T omega. So it is 150.52 into 120 radian per second. It is coming as 18542.7 watt. Okay, this is your answer. Next, a propeller with a diameter generates a thrust of this while moving through air at a velocity this. Find the velocity of the air in the slipstream downstream. So we can calculate the mass. So mass is pi by 4 area into rho into velocity, right? So it is pi by 4, d is 2 square, rho is 1.225 into u is 40. So it is n is coming as 153.86 153.86 kg per second. It is mass per flow rate, right? Now solve for the velocity increment. So velocity increment has happened like P equals to m dot into u, right? So u is T by m dot. So it is coming as 32.49 32.49 meter per second. Find the velocity at the downstream, that is u plus u, then coming as 50 plus 40 plus this. This is 72.49. It is coming as 72.49 meter per second. Next, in a jet pump, a high-velocity water jet is discharged through a nozzle of diameter this into a larger pipe of diameter. The surrounding water velocity is this. Calculate the pressure increase created by the mixing. So it is the jet pump pressure formula is P2 minus P1 equals to rho into small d square by capital D square, and capital D square minus small d square by capital D square into V0 minus V1 square. So we will just calculate every term now. So rho is given as water. So 1000 into 0.05 square by 0.15 square, 0.15 square minus 0.05 square divided by 0.15 square, and this is 40 minus 5 whole square. So it is coming as 1,20987.65 Pascal, right? Next, which of the following describes the primary physical principle used by Venturi meter to measure the flow of rate? So it is the option B, converting pressure head into velocity head through a constriction. Next, in a horizontal Venturi meter, how does the pressure at the throat, that means the narrowest part, so Venturi meter is kind of this, right? Compared to the pressure at the inlet. So it is the throat pressure is lower because of the velocity is higher, right? Next, why is the total energy line of for a real fluid in Venturi meter usually shown with a slight downward slope? Because in real fluid, we have to consider the energy losses such as friction. Option C. Next, so there is a problem on Venturi meter. So a horizontal Venturi meter is used to measure the flow of water. In the inlet diameter is this, the throat diameter is this. If the pressure at the inlet is this and the volumetric flow rate is 0.06 meter cube per second, calculate the velocity and pressure at the throat. So you have to first calculate the A1, like velocity V1. So from same pi d square d1 square by 4, it is coming this q by pi d1 square by 4, right? So q is your 0.06 into 4 by 114 by 0.3 whole square. It is 0.849 meter per second. 0.849 meter per second. Next is V2. Similarly, it will come as it will come 3.396 meter per second. So, from the Bernoulli equation from the horizontal, so it is coming as P1 plus half rho V1 square equals to P2 plus half rho V2 square. So P2 will be P1 plus half rho V1 square minus V2 square. It is coming as nine 4.59 kilopascal. That means it is coming as actually 94593.9 Pascal, right? And this is the velocity answer. Last question is again about this Venturi meter. A horizontal Venturi meter has an inlet diameter of this and a throat diameter of this. The pressure difference between the inlet and throat is measured at 20 kPa. Calculate the discharge Q over of water through the meter. So from A1 V1 we will get the ratio of V1 and V2. So A1 V1 equals to A2 V2. So A1 is pi 200 square by 4 V1 equals to pi 100 square by 4 into V2. Right? So V1 equals to 100 square by 200 square, right? It is 0.25 into V2. Now from Bernoulli's equation in the horizontal direction, you already know that P1 minus P2 equals to half rho V2 square minus V1 square is given. So P1 minus P2 is given as 20,000 Newton per meter square equals to half into rho is about water, that is 1000, and V2 so this is V2 into minus, so if you common V2, no, that means V2 square minus 0.25 V2 square, so it will be coming as 20,000 into 2 by 1000 divided by 0.75, so root under this will be 7 point. Okay, so this is V2 square minus 0.25 V2 square, so 0.25 the whole square means, so this is coming 20,000 into 2 divided by 1000 divided by 1 minus 0.25 a whole square, that is coming as 42.6. So root under this is 6.532. So V2 is coming as 6.5319 meter per second. Now your Q will be pi into 0.1 square by 4 into 6.5319 equals to 0.05127 meter cube per second. This is your answer. Okay, so for today's class, this is, I hope you have found this discussion good enough for solving your problems. I have discussed the core equations of conservation of mass, conservation of linear momentum, and conservation of energy in a different way from what has sir taught, because it will be much more easier to remember how from where the equation is coming with the Reynolds transport theorem and the subsequent problems what I have solved. So you have to remember these equations little bit, because Bernoulli's equation is a very famous equation, so you need to remember this so that you can apply anything, any formula towards it, right? So we'll meet in next Friday. Till then, goodbye. Thank you.